Hi, I'm Dr. Alexander NGENZI from University of Rwanda College of Science and Technology, Department of Computer and Software Engineering. Good morning, dear viewers. Good morning, everyone. Today we are going to start a new chapter, which is chapter 4, and it is all about the first Fourier transform. And the first Fourier transform is the enhancement feature of DFT, which was discrete Fourier transform, and it's going to have the following points. We are going to discuss the following points. First of all, we will revise or do some revision on what we saw on DFT algorithm. We are also going to discuss about the first Fourier transform algorithm itself, and deep I mean. We will also discuss about decimation in time domain, or first Fourier transform, of course. We are also going to discuss the radix too in both DFT and FFT. We will also discuss about the how do we reduce all the number of computations in first Fourier transform. We also discuss about the radix in decimation in time domain in DFT only. We will also discuss about the 2-point in DFT domain. We shall also discuss the comparison between the DFT and the FFT algorithm in terms of just reducing number of computations. We also discuss about the radix 2 and the radix 4 with 4 points. So in this case we are going to discuss about the 4-point FFT, which is first Fourier transform, and lastly we are going to discuss about the decimation in frequency domain. So all those are going to be the ingredients of the chapter 4, which is first Fourier transform. So and this is going to be the first portion is going to be reduced in a few minutes so that people can understand the concept. So it will be like a portion, I mean the 2 parts, the 2 parts or 4 parts, depending to which time we have, and we are sure that we are going to be one of the you are going to support us in this. We are going to interact a lot and just get the focus on this subject. So thank you for just being with us. Yeah, as I said in my introduction, we are supposed to begin with the DFT algorithm, but you remember we discussed it last time. Maybe we shall have to repeat again so that people can understand. But in this at this point, we are going to have some retro explanation about how do we are used to know to discuss about DFT. But also today we are going to also to add FFT, which is our main topic for today. So in DFT, remember, if you can recall very well, we said that it is the easiest way of just converting the discrete values into their corresponding frequency domain. But in this case, we are focusing on the number of computations. So the number of computations in this case are going to be slightly very fast, because we are using first Fourier transform, and it's going to be reduced somehow, so that if the number was very huge, then it is going to be reduced somehow so that the computation is going to be fast. So that's why we are introducing fast Fourier transform in this case to enhance the features of DFT so that we can have a very good results after our computations. So the fast Fourier transform is the best known technology or phenomenon that is going to deal with discrete transform, which is DFT, of course. So in this particular chapter, we are going to discuss about how does fast Fourier transform enhance the features of DFT, and what is this what is new in FFT, and how is it going to help in the calculations of our, or if given a problem to solve. So first of all, in this case, we are going to see how the fast Fourier transform is going to help us to allow the reduction of or reducing number of computation in the corresponding DFT. So first of all, it's going to allow the adequate representation of, going to allow the adequate representation of DSP or digital signal processing, or in the frequency in the frequency domain. So remember, last time we discussed about some of the formulas, as we will also continue to discuss about them. They are very important throughout this course. So another one that we are going to discuss is about how is it applied, the application of Fourier transform in digital signal processing. It can be used, it is applied, and it is applied or its application applied in spectral analysis. What do we mean by spectral analysis? Remember, we are looking for the frequency. We have number of computations in discrete format. They are in numbers. But we remember, in this case, we are trying to bring together number of frequencies in their spectrum, so which is a spectral analysis, and see how many number of frequencies that we want, and how many computational numbers that we are going to do, and how do we come up with the concrete results in our analysis. So remember, before just having this computational, the computational in the frequency domain, remember for the first one, where it is applied in the spectral analysis in the frequency domain, it should be in frequency. So the frequency is to have to reduce the number of computations, so that it is reduced. The complex numbers that we have are going to be reduced. And here also, if you can recall very well, number one, the reasons having a DFT. Remember, the DFT is the first algorithm before having the first Fourier transform. So the discrete first for Fourier transform is the first to be analyzed. And remember, the reason was to allow to determine the frequency contents. So this is FFT, for example, FFT. But here also can reasons for, we can discuss the reasons for DFT, and that is a reminder. It's to recall, to remind you what we discussed last time. The reasons of DFT, number one, was to allow the frequency, the content, a signal to be performed in the spectral, in their spectral analysis, or the spectrum. So it was to allow the computation, or the computations of frequencies in their spectrum, or spectrum, spectral. So that is analysis, spectral analysis that we talked about there. So we analyze spectral analysis in this case. So that was the reason to get to understand what was the use of DFT. So that is reason number one. Another reason was about to perform the filtering operations. So another reason was to perform filtering. Sorry, this is N, big N. Filtering operations. So remember, throughout this course, we discussed how the noise signal, the distortion, the interferences, all those disturbances that can happen during the signal processing can be can be reduced or just totally removed. So in this case, when we are using filter, as we shall see in its own topic or in its own chapter, it's going to filter out the required signals, the required signals, and just the residues are going to be jumped down somewhere. So we want our signal to remain as pure as possible, so that the signal can have the impact or the outlook that is suitable for future use, for example, or for any digital analysis or any publications or research. So the filtering is going to the filter is going to play a big role to have such a results. So it's going to filter out the unwanted signals. Remember, those crosstalks, noises, interferences, and distortions are going to be removed, so that we remain with our pure signal. So the reason here that's why we are talking about the filtering operations, so that the frequencies with noises, with crosstalks, with interferences, with distortions can be removed and remain with pure frequencies. So, and these are the reasons that we should remember in just complying with the FFT, which is the first Fourier transform. Remember, the use of FFT is to reduce the number of computations by using the first Fourier transform, and remember, transforming the discrete value to their corresponding frequencies, so that the frequencies can remain as pure as possible. So another point that I want to make here, remember, when you are just putting you are trying to create a spectrum or the spectral analysis, we are trying to compute the n times the big N times, or N point in this case, so that each frequency is treated separately, and also having after that you just combine them by using the formula that we showed last time. And if you can recall very well, we had suppose if we have xn in discrete format, so we want to transform it into big X of k, and big X of k, as we explain, it is summation from n is equal to 0 to big N minus 1 of the value of xn in this case, and then power, depending to which the denotation that you want to use, for example, minus j 2 pi n k over big N. This is the general format, the general formula that we are going to use, so that we can have our computations results, so that we can obtain our computational results. So remember, k can range from, for example, any value from 0, 1, 2, 3, so on, until it reaches for n minus 1 endpoint in this case. So this is very important to note. So I'm just reminding you what we discussed in DFT. This is a DFT format, and it is done with a finite number, not infinite number. That's why we began from 0, so that the numbers cannot have this element of infinity, so that we can. So they are computed or calculated with their finite durations. So the number of times here are known, which is in this case showed by n times, or defined by n, number of times. So in this case we are going to so that's why you see that there is no infinite number. The numbers are known from any particular point. So that this was discrete. So I'm just reminding you the way how these computations are done. Remember, you can easily compute DFT using this formula, but also you can get the vice versa. You may need to get the frequency, which we are discussing today, but also the vice versa. Remember, when we are using IDFT, which is inverse discrete Fourier transform, it's going to be the other way around. It's going to be the x of n in this case is going to be 1 over n, which is inverse of the number of times, and it's going to be the summation of n, of course. In this case, it's going to be n from 0 to big N minus 1. And remember, what's going to be here? It's not going to be this, because it's going to be the big X of k in this case. And the main coefficient is going to be the same, j 2 pi n k over big N in this case. So this is going to be the inverse DFT. So these formulas, the reason why I'm putting them here is to remind you that when computing the number of n times, or the number of the time durations, or the finite duration or infinite, it will depend to these formulas. So this is the normal equation, and this is the inverse of it. So, and here, despite of using this one, in this case it's going to be n ranging from 0, 1, 2, 3, and so on, up to, of course, it's going to be n minus 1. Remember, this is very common for n times. So these equations are very useful in our formats. Yeah, so in this case, if you can, and here to make sure that all these are respected, coming to our outlines that as I introduced in our chapter, now we are going to start with the DFT algorithm, which we discussed even before. Remember when we were discussing the properties like multiple properties, multiplication properties. We discussed about the additional properties, where we said last time that there is a number of computation in case when there is n times for multiplication properties. Remember, we had n squared as its notation. Sorry. In this case, for addition property, remember we discussed about how n into n minus 1 property. So we use this to get a number of big n's. And remember, we also substituted it by using, instead of using e power j2 pi n and k of big N, we used wn big N into nk. This was the notion when you want to use these properties. So all these properties are discussed in DFT algorithm of what we saw last time. So the last time we discussed about DFT algorithm, where we got these notations and the conversions. So, and this reflects of what I discussed from my first point, and by saying, by talking about the number one is going to be a review of DFT algorithm. So this is the point that we are going to discuss now, according to the outlines that we have. Is to review what is a DFT algorithm, so that it can take us to the first Fourier transform algorithm, whereby it will be a little bit enhancement of what we saw in DFT algorithm. So as you can recall very well, we have also summarized it in our introduction. So if you can see this this portion, we said there's no way how you can compute number of times or number of computations in frequency domain without even reminding you how these formulas were made. So the first formula was a DFT formula, and the second one was an inverse DFT. So this is a DFT formula that takes us here, where k is equal to ranges from 0 up to n minus 1, and the second formula here is going to be the inverse of it. So the reason why we are bringing them here is to see, in case when you are given any problem, how do you solve that problem given any particular calculations or any complex number in one of these. It may be its inverse, then they want you to convert it into their DFT domain. It can be DFT domain. You want to convert them into their corresponding inverse domain. I mean inverse using this formula of inverse computations.
Remember, if you are doing inverse, you are taking you will be having frequency domain, which is going to be converted into their corresponding numbers, the digital numbers. So the digital numbers can also be transformed into their frequency domain. So the inverse, you are trying to take them again to their discrete value. Then the normal DFT is taking you from discrete value to their corresponding frequency domain. So, and this is very common in this case. So I was talking about the DFT algorithm. So this is what I was discussing on this case. So in DFT algorithm, we can remember, we discussed about the complex multiplication property, which is n squared, given a number of computations in terms of n. There is also complex addition, which is n into n minus 1. So now we are going to continue according to the outlines that I have mentioned from the beginning. We were supposed to begin with DFT algorithm. Of course, this one we discussed it last time. We are not going to spend much of our time on this. So it's just a reminder, as I said. We said the sequence of values can be decomposed or be divided into a simpler different frequencies. So if we have a discrete value, so it can be decomposed into their corresponding frequencies using DFT, of course, into their corresponding the frequency domain in this case. So using this one, you obtain each one of, so it's inverse again, IDFT is going to be the inverse from this domain to the other one. So this is applied everywhere, and if you can recall, I showed you the DFT, which is the signal that I showed you. I said in its DFT, we are going to have x of k, which is equal to, we are repeating this one so that people can understand it easily and get the full meaning of it. So in this case, this is DFT. I'm repeating it again so that it goes in hand with what you are trying to explain. So IDFT, which is this one, is going to be x of n, of course, so that you get this formula 0 big N minus 1. In this case, is going to be the frequency domain big X of k e power j 2 pi n k over n. So we are going to use this formula so that we can remind how DFT algorithm was done. In this case, it is a simple summary of what we saw last time. So remember, if you can recall the previous explanation that I showed you, we have two different ways. So first of all, the DFT algorithm is going to decompose the values of discrete numbers into their corresponding frequency domain. So as you can see in the formula, you have discrete values, the discrete values. Then you want to get the different frequencies. And this is the essence of just having this algorithm. So remember, there are two ways to compute this, to get this discrete value. So number one, we said complex multiplication property, which is n squared, and we can also have number two, which is complex additional property. Additional property, which is big N into n minus 1. So these are going to help us. So the DFT algorithm is going to have to concentrate on these points, the way how we obtain this one. And remember, we discussed this one. It is a repetition, where we said, in case where we said x of k in this case is a summation of from n to n minus 1 into small x of n e power j2 pi k over n. And this one also can be, remember this portion can be replaced by saying x of n equal to n of 0, n minus 1 of small x n of big M, big N, and K in this case. So you can replace this one into W N K. And remember, K is ranging from 0, 1, 2 into N minus 1. So this is very common to DFT algorithm. So this is like a summary of what we saw last time. We are repeating it for the time. So, and why do we want to bring this kind of FFT in this algorithm? Remember, when we compute using this algorithm, we are trying to calculate the number of computations here, which are very big in number. And this one is a time consuming. It takes a lot of time. It takes a lot of time, so that when computing, it will just take huge time to overcome or to get the results. So, and that's why we bring the context of fast Fourier transform, which is going to reduce those numbers of computations. So in this case, this algorithm, that's why we wanted to bring it on the board, so that we see its disadvantage, and then after seeing its advantage, how do we overcome those advantages? So that, and that's why the point of FFT comes in. So to summarize what I have discussed on DFT algorithm, first of all, remember we are trying to compute discrete value into different frequencies, into their corresponding frequency domain. That is what you should understand, first of all. Another one is that we are going, in the DFT algorithm, we are going to consider two main operations here. First operation is going to be the complex multiplication property, whereby we get n squared. And the second one is going to be the complex additional property, which is going to be n into bracket n minus 1 property. So, but the reason why we want to bring in fast Fourier transform, you see all these computational that you have been discussing, is that we have big numbers of n. And having a large number of n, it is a time consuming, first of all. So it is going to have a huge period of time to overcome all this, to get the solution for those big numbers of n times. So to overcome that, we bring it FFT on board, so that it can reduce all those number of computations, and also and therefore reducing time. So we are the next portion is we are going to discuss the first Fourier transform algorithm itself.